In this video, we'll look at measures of nonlinearity and dynamic range applicable to CMOS amplifiers. Typically, we seek to use amplifiers as linear systems, but since transistors have nonlinear IV characteristics, inevitably some nonlinearity will creep in. When we're considering this nonlinearity and seek to quantify it, let's consider a memoryless model for nonlinearity, that is, one for which the instantaneous output of an amplifier is a function only of its current inputs. Here you see a polynomial expression for Vn, modeling the nonlinearity in an amplifier. And you'll notice that the output at time t depends only on the input at time t. That's why we call it a memoryless nonlinearity. In an analog circuit, this is an approximation to the full Volterra series required to capture frequency-dependent nonlinearities. A Volterra series is a nonlinear relationship between the output and both current and past values of the input voltage Vin. Such descriptions are complicated and preclude closed-form analysis in many cases. Moreover, this memoryless nonlinearity model will allow us to develop intuitions that are observed in practice, even in the presence of nonlinearities with memory. So normally with a model like this, the distortion terms get smaller. So the linear term is dominant. That's what allows us to, for the most part, assume that the amplifier is a linear system. The coefficient A1 is usually the largest coefficient, and A2 and A3 and A4 get smaller and smaller as we go down, including more and more terms in the nonlinear relationship. There are some exceptions that we'll discuss soon where we see that even order distortion terms can be smaller than odd order distortion terms, but generally the trend is towards smaller and smaller distortion terms as we go to higher and higher order terms in Vn. But you'll notice that the higher order terms increase faster with increasing input amplitude. So for example, Vn, this term here, Vn squared, will grow a lot faster than the linear term as Vn increases. So for a large enough value of Vn, this term will become significant and even eventually dominant. But for small inputs, only the linear term remains. Total harmonic distortion is a measure of nonlinearity. It measures the ratio of fundamental signal power to that of all the harmonics. So it would be measured by applying a pure single tone input to a nonlinear circuit. As a result, our memoryless model would predict that we see a fundamental term that's just a gain A1 times the input sinusoid, plus nonlinear terms that give rise to harmonics at integer multiples of the input frequency omega. Labeling the amplitude of the fundamental HD1 and that of the harmonics HD2, HD3, and so on, we can take their ratio as shown here. Expressing it in dB gives us the total harmonic distortion in dB. You'll sometimes also see THD observed as a percentage. The THD measurement is straightforward to perform only when the fundamental signal frequency is well below the circuit's upper passband limit. The reason is that if you supply an input tone right around the high frequency limit of the amplifier's bandwidth, then the harmonic terms will lie beyond the bandwidth limit of the amplifier, and as a result, they're likely to be attenuated. This gives rise to an optimistic value for total harmonic distortion that underestimates the amount of nonlinearity present. Now you might say if the harmonics are attenuated by the amplifier's upper passband limit, all the better. It means that the output looks more like a single tone, and doesn't that mean it looks perfectly linear? But in general, we may not be interested only in pure sinusoidal inputs. You may have a combination of frequency inputs, and those at the upper band limit may combine with nonlinearities at lower frequencies and give rise to an overall output spectrum that's corrupted with nonlinearities. That's why THD is only a useful metric of amplifier linearity when the input tone is well below the upper band limit of the amplifier, so that at least the first couple of harmonic terms also lie within the amplifier's bandwidth. Now, if we focus on just the first three terms of this memoryless nonlinearity model, and we consider the case where the input is a cosine waveform with an amplitude A, then we can find that the output is got the linear term, the gain of A1, then there's the squared term, which using some trig identities, you can see gives an expression like this. And then you've got the cubic term, finally. You see, you can identify the terms by those coefficients A1, A2, and A3. And what you find is that the linear term gives rise to the dominant tone at the fundamental omega frequency. Although there's another fundamental term showing up here, it's going to be a lot smaller than the main fundamental term over here, as long as the input amplitude's not too large, because A1 is a lot bigger than A3. Now, as the input amplitude grows, A, capital A, then eventually these other terms will come into play, but that will be at such large amplitudes that the amplifier is grossly nonlinear at that point, and it's probably not useful anyway. So for all amplitudes of interest, the dominant linear term will be the 1 due to the linear coefficient A1. Similarly, the dominant second order term is coming from the squared coefficient, A2, and the dominant third order harmonic, HD3, is coming from the cubic term. So we'll sometimes refer to these terms here as a first order term gives rise to the fundamental, the second order term giving rise to the second order harmonic, and the third order term giving rise to the third harmonic, HD1, HD2, and HD3, respectively. Fully differential circuits are those for which the input is applied to one copy of the circuit. Let's say, for example, a simple common source amplifier, as shown here. And a negative version of the input is applied to a precise copy of the same circuit. So if our input signal is V1, we can apply negative V1 to a copy of the common source amplifier. And then, again, in a fully differential circuit, we take the output as the difference between the outputs of these two half circuits. So in this case, let's call the output VDiff. So over here, we've got 1/2 the output, and over here, the other half of the output. Now, a common example of this that you've already seen is, of course, the simple differential pair with the output taken differentially. In that case, we just use a tail current to provide some common mode rejection. But otherwise, the half circuit looks just like two common source amplifiers. And of course, we've always got to apply a DC bias common mode voltage to both half circuits to keep the transistors operating in active mode. But in any case, the picture can be considered the one shown here on the left, where V1 is applied to a nonlinearity that may be modeled with a polynomial, and negative V1 is applied to the exact same nonlinearity, and we can use the same model for it. We're neglecting here some mismatch, which should be a relatively small fraction of the overall output, of course. So you'll notice that our nonlinearities in these two cases include all harmonics, second, third, fourth order terms showing up in both VP1 and VN1. But interestingly, all the even order harmonics have the same sign, because when you raise something to the second power or the fourth power, then negative V1 becomes plus V1 squared plus V1 to the fourth, and so on. So then, when you take the difference between the two half-circuit outputs, all the even order harmonic terms cancel each other perfectly. And you're therefore only left with the fundamental and all odd harmonics at the output. Again, we've neglected some mismatch, which would, if taken into account, give rise to a small even order distortion terms. But certainly it's the case that this third order distortion terms becomes the largest at the output. Here's a relatively simple example showing cancellation of even order distortion in a fully differential circuit. We've got a fully differential input applied to a pair of track and hold circuits formed by a simple MOS switch and a capacitor C. Then these are simulation results with real transistor parameters, such as the ones shown here. The circuit's nonlinear because the transistors in triode are not perfectly linear. With any VDS appearing across them, then we're going to exercise the transistors' nonlinearities. And a VDS will arise across them, especially at higher frequencies, because the low-pass nature of the RC network formed here means that the output amplitude will be a little bit less than the input amplitude at high frequencies. So at a particular input frequency shown here, you can look at and a sinusoidal input applied at Vn and Vn minus. Then if you look at just one half of the output, just V out plus in this case, you see the fundamental term is the largest. You see the second largest term is the second order term, second harmonic HD2, and then the third order harmonic and fourth order harmonics get progressively smaller. However, if you consider the output differentially, that is, you take V out plus minus V out minus, then you see the second order harmonic disappears completely, whereas the third order harmonic remains. And what the reason for this is that V out minus is a precise copy of this spectrum, but what's not shown here on the spectral plot is the phase of the output. We're showing only the magnitude of the spectrum at the output here. So it turns out that the even order terms have, at V out plus and V out minus, have phase relationships that allow them to perfectly cancel when we take the difference between V out plus and V out minus, whereas the odd order harmonic terms add up constructively, just like the input fundamental does. So they remain. So in the differential output, for a properly designed fully differential circuit, it's typically going to be the third order harmonic that is the dominant one. Whereas if you've got a single-ended circuit, it's typically the second order harmonic that's the dominant one for any reasonable input amplitude that makes the circuit still behave predominantly linearly. Now in practice, this cancellation is never perfect. There's always going to be a little mismatch between the two half circuits. So here, for example, we repeated this example, but including a small threshold voltage mismatch between these two transistors of 10 millivolts. And what you see at the differential output now is typical for what you might find in a real simulation, including mismatch, or in a lab environment. And that is that you do see some even order harmonic terms. The second order harmonic is still there here, but that if the circuit is well designed and the matching is decent, the third order harmonic will still be larger, will still be the dominant one. So in summary, if we consider the THD of fully differential circuits, total harmonic distortion, we may approximate it by considering only the linear and cubic terms of the memoryless nonlinearity, and then we would see that the amplitude of HD3, the third order harmonic, is given by A3, the coefficient of the third order nonlinearity, A cubed divided by 4. So that's the amplitude of the third order harmonic HD3. In the presence of some mismatch, there will still be a finite HD2, but it should be smaller than HD3. So when we take the ratio of HD1 to all the harmonics, this term will predominate, and you'll end up with just the ratio of HD3 over HD1 being approximately equal to the THD. And so that ratio is expressed here. And of course, we might express it in dB as well, or in percentage. Now, there's a little bit of notation here. Just note that we're using the uppercase H with the subscript D3 to denote the amplitude of the third order harmonic at 3 omega, but we use the uppercase HD with subscript 3 to denote the ratio of that third order harmonic to the fundamental, which, again, in the case of a properly designed fully differential circuit, will approximately equal the total harmonic distortion. Now, a key point here that you'll notice is that since the third order harmonic grows with A cubed, but the linear term just grows in proportion to A, then HD3, and you end up seeing cancellation of one of the A terms, and you end up with an HD3 that's proportional to A squared. So if you imagine an experiment where you apply a very small at first sinusoidal input to an amplifier, and you gradually start increasing the amplitude A at the input, what you would see is that the output fundamental would grow in proportion, but the dominant third order harmonic would grow much faster. And so the THD is going to get worse with the square of the input amplitude A. If you're looking at the spectrum of the output, what you would see is HD1 would grow a little, HD3 would grow more, HD1 would grow a little more, HD3 would grow more, so that the gap between them, which on a log scale is actually equal to HD3, would shrink as the input amplitude increases. So as we mentioned before, that when you try to measure THD with input tones near the circuit's passband edge, distortion terms are filtered out. So let's say that the amplifier has a low pass response given by this dashed line, and the input tone is applied here at omega. You'd see that the third order distortion term certainly lies out of band and would therefore be attenuated. And again, that would predict a very high THD and give an optimistic view of the circuit's linearity. But in general, with a broadband input waveform, such high frequency distortions may mix with lower frequency tones in band. So for this reason, single tone measurements may not accurately capture the linearity performance of a circuit at all frequencies, especially when broadband inputs are required in practice. So this is a problem also when measuring bandpass circuits, that is, circuits that exhibit gain over only a narrow range of frequencies. In such cases, it's practically impossible to capture the linearity performance using just a single tone input. That's the motivation for performing two-tone testing, where the input is not just a single sinusoid at omega naught, but the superposition of two sinusoids at closely spaced frequencies, omega 1 and omega 2, and with the same amplitude, A. Two-tone measurements address this problem by measuring third-order distortion terms by looking at the intermodulation of these two tones at the output. Specifically, let's recall our memoryless model for nonlinearity. We've got a linear term And let's assume a fully differential circuit so that we need only consider the third order term. And if you substitute into this expression the two-tone input shown here, and you work through the trigonometry, what you see is that you do get the third order harmonics of each input tone, 3 times omega 1 and 3 times omega 2, but these are likely to lie well out of band of the amplifier, and so again may get attenuated and are not a good measure of the circuit's nonlinearity. However, you do get these tones here, which arise on either side of the input frequencies at omega 1 minus delta omega, where delta omega is the difference between these two input frequencies, and at omega 2 plus delta omega. That's why we take the input tones at omega 1 and omega 2 closely spaced, so that at the output we see these small terms relatively close to the input frequencies omega 1 and omega 2. We can put omega 1 and omega 2 right up against the upper bandwidth limit of the amplifier, and still these so-called intermodulation products will still show up in band and therefore not get attenuated. Now these extra tones, these intermodulation products, have an amplitude that varies in much the same way as the amplitude of the third harmonics. That is, you see very similar coefficient up front. You see A3, so the larger the third order nonlinearity, the larger the intermodulation products will be. And you also see that they grow in proportion to the input amplitude A to the power of 3. So just like the single tone testing, where we looked at the third harmonic, we see that these intermodulation products grow faster than the fundamental tone at the output, so that this distance here on a log scale will shrink as input amplitude increases. This type of two-tone testing allows you to measure linearity by stimulating the circuit at very high frequencies at the upper limit of its bandwidth. This can be important because some types of nonlinearity are frequency dependent, and although we've derived this result assuming a memoryless model, the very same behavior is observed when we consider nonlinearities with memory. And because many types of nonlinearity get worse at high frequencies, we really do want to test nonlinearity over the entire frequency range of operation of the circuit. This type of testing is especially important when we have bandpass amplifiers, where single tone harmonics will always lie out of band. So again, let's imagine an experiment where we're taking an amplifier that has some nonlinearity and we're applying input, either a single tone or two-tone input, with an amplitude having an input level A. And let's imagine that we sweep the input level of the input amplitude. And as we do so, we move from left to right across the x-axis on this plot. And on the y-axis, we're going to plot the amplitude of the fundamental tone observed at the output, tone or tones in the case of two-tone input. And we make a second plot that is the amplitude of the third order harmonics for a single tone input, or the intermodulation products for a two-tone input. So in either case, we would see that the fundamental terms increase on a log-log scale with a slope of 1, because the output fundamental is proportional to the input signal level. Now, where this curve lies, whether it's shifted up or down, will depend on the gain of the amplifier, but it will always have a slope of 1 for the linear terms at the output. However, the third order terms, again, these are the third order harmonics for single tone input or the intermodulation products as shown over here. For a two-tone input, those will increase in proportion to A cubed, and that will show up with a slope of 3 on a log-log scale. So the difference between these two plots is a measure of HD3 for a single tone input, or what we'll label ID3 for a two-tone input. We follow a similar notation as we did for single tone input, except instead of HD, we label the intermodulation terms ID, and the subscript 3 denotes that we're interested in the third order intermodulation product. So taking the ratio of these, we again get a very similar expression to what we had for HD3. There's just this extra factor of 3 that shows up in the intermodulation product. So we see that the ratio of the fundamental to the third order harmonic gets worse with the input amplitude A squared. So that captures the fact that the distance between these two plots on a log-log scale is ID3. And in fact, if the axes here have units of dB, dBm in both cases, being a power unit, then we can simply read off the distance here as the ID3 term in dB. So another problem with using either HD3 or ID3 as a measure of nonlinearity is that clearly, looking at this plot, it's going to vary with input amplitude. If we measure ID3 at this input amplitude, we're going to get a larger value than if we measure ID3 over here to the right. So if we're thinking about trying to quantify the linearity of an amplifier, what we're really interested in is kind of how far apart these two plots are. They're always going to get closer and closer together. So if the input amplitude is large enough, they're always going to be close together. And if the input amplitude is small enough, they're always going to be far apart. But we need some kind of measure of really how far apart are they. And one way we can measure that is how far do you have to go to the right here before these two plots come together. Now the reality is that you would have to increase the input amplitude so large in general to make the third order nonlinearity actually equal to the fundamental that by then the circuit's going completely haywire and other saturation effects kick in. So we usually can't measure or simulate all the way to the point where these two plots come together. What we can do is apply relatively small input amplitudes and establish the straight sections of these plots, and then extrapolate that line out to the point where they would intersect. This intersection point is called the third order intercept point because we're focused here on the third order nonlinearity, assuming that the circuit is fully differential. You can also define the second order intercept point if it's a single-ended circuit. In that case, this plot here would be a plot of HD2, and it would be increasing with a slope of 2, but similar definitions would apply because eventually taking the linear portions of the two plots and extrapolating them out would result in an intercept point. So having identified the intercept point over here, we can now quantify the linearity of the circuit in terms of the input amplitude required to get to this intercept point. That is the so-called input-referred intercept point. And since here we're focused on the third order nonlinearity, we call that IIP3. Or similarly, we can define the output intercept point as the output amplitude observed at the intercept, OIP3 in this case, because we're focused on the third order nonlinearity. These two are related. Now there's a handy expression here that just takes advantage of the fact that if you measure the ID3 at any one input amplitude, as long as you're on the linear part of this plot, that is the portion of the plot where these two lines have are straight, then you can just extrapolate out to the intercept point from just one measurement by assuming that they are coming together from this one measurement point with the square of A. So the fact that they're coming together with the square of a gives rise to this 2 in the denominator, and we just take the distance between these two and the ID1, that is the amplitude over here, and extrapolate out to the right to get the OIP. So if we consider the fidelity of the output of an amplifier as a function of its signal swing, clearly as we increase the signal swing at both the input and the output, the signal-to-noise ratio is going to improve because the noise sources won't change much with input amplitude. However, we've seen that increasing the input amplitude causes the distortion terms to grow faster and measures of linearity such as THD to get worse. And eventually there's some upper limit of signal swing where those nonlinearities are so bad that the amplifier is no longer useful for us. So the maximum signal amplitude that we can use our amplifier with is limited by the tolerable nonlinearity in our application. On the other hand, if we decrease the input and output amplitudes, the linearity just gets better and better. The THD improves, and this is our so-called small signal assumption. That is that for small enough signals, the circuit behaves just like a linear system. However, eventually, the signal amplitudes are so small that they're swamped by the noise in the circuit. So the minimum signal amplitude for which our amplifier is useful is limited by the tolerable SNR in our application. Dynamic range is a measure of the distance between these two. So you can imagine one circuit may be able to handle really large signal amplitudes but is very noisy, whereas another circuit gets very nonlinear very quickly but has very, very low noise. So those are two very different circuits with two different applications, but they might have very similar dynamic range. So far we talked about dynamic range in qualitative terms, but it's always nice to have metrics that allow us to quantify these things. One way to quantify dynamic range is in terms of the so-called spurious-free dynamic range, or SFDR. This is defined as the signal-to-noise ratio, where the power of the largest distortion terms, sometimes called spurs for short, or spurious tones, because they're tones that arise at frequencies other than the fundamental, the SNR at which those spurs power equals the noise power evident at the output. So the SFDR can be read off this plot where we've swept input amplitude on the x-axis and plotted the output components on the y-axis as shown here. We just have to put notches at the input referred noise and the output noise of the circuit here. And if we identify the point at which the third order distortion, in this case being the dominant one, assuming a fully differential circuit, surpasses the noise floor here, right at that point there, then the output signal amplitude is up here. So the gap between the output signal amplitude and the noise floor is the SNR, and that's exactly the same as the ID3 in this case, because the third order distortion term is right at the same level. So this gap here then is the SFDR, the spurious-free dynamic range. You can see this plot is also useful in other ways too. You can also use it to measure SNR at different amplitudes. As we're sweeping the input amplitude, we see the SNR increases, and but the ID3 is getting worse. The ID3 meaning this distance here. So you can think of the SFDR as being the point at which the SNR, the red gap, is exactly equal to ID3. The signal to noise and distortion ratio is also useful in quantifying dynamic range. You're probably already familiar with the signal-to-noise ratio, where we would take, for a single tone input, the power at the output of the fundamental and take the ratio of that to the power of the noise at the output. Now, signal-to-noise and distortion ratio simply adds to the noise power the power of all the harmonics. And we would expect in a single-ended circuit this term to be dominant, in a fully differential circuit this term to be dominant. But for generality here, we're just showing all the terms. So what you see is kind of a combination of signal-to-noise ratio and THD over here. So following the intuition we described previously, at first for very small input amplitudes, plotted here on the x-axis, we would see that the SNDR simply improves, because in this part of the plot, the output noise is a lot greater than all the harmonic terms. So that being the case, then the SNDR over here is dominated by the first term of the denominator and is approximately simply equal to the SNR. As we expect, higher amplitude gives better SNR. But at some point, the distortion terms would start kicking in and being dominant. This could be the second or third order distortion terms, depending on whether it's a single-ended or fully differential circuit. But at this point, the noise term would be negligible in the denominator, and we would see essentially THD plotted here. SNDR would be approximately just equal to THD, actually the inverse of THD, the way we defined it previously. And we know that THD gets worse with increasing amplitude. So there is a sweet spot in between there where the noise and the harmonic terms are comparable in size, and that gives us the maximum achievable signal-to-noise and distortion ratio. That itself is a popular metric for quantifying the dynamic range of an analog circuit.